Hello guys, nice to see you.
Good afternoon.
Good afternoon. Hi. So last time we introduced a new concept and like phenomenon, which is interference of light. Hello. Yeah, nice to see you. And we considered this experiment with two slits interference, considered conditions for so-called constructive and destructive interference. Also derived equation which analytically describes distribution of light intensity for this interference pattern. So these conditions for constructive and destructive interference gives us exact angular or linear position, like coordinate of the middle of bright and dark fringes, but light intensity is changing gradually. So we also calculated how this light intensity will change as a function of angle or position along the viewing screen. So also we need to consider other options for interference. It's not only a two-slit experiment. And today we will finish our discussion of interference, which actually is the last topic to be covered in our course. Let me switch our camera. And first option for interference, which we will consider, is reflection. The key requirement to get interference effect is to create certain path difference for two beams of some monochromatic light, and create, because of this path difference, certain constant phase shift between these two waves. So we can organize interference effect considering such a system. When we have mirror, there is some point source of light, like monochromatic light. Then we have viewing screen. And here will be some point P, where we want to observe the result of superposition of two waves. So one will just travel straight to this point P, and another will reflect from this mirror, horizontal mirror. So we get here, here, then it reflected, and reaches the point P where we should observe it. In this case, it appears that this reflected beam originates from some imaginary source, which position can be determined by extrapolation of this reflected beam towards the plane where original light source is located. So this is our imaginary light source S prime. And there will be some distance between the original light source and its kind of imaginary light source. So that distance d. So then we can follow the same consideration of this interference, considering kind of which was applied for two slits interference experiment. However, here the interference pattern will be kind of flipped over. We will have black lines were supposed to be bright, and in the contrary, bright were supposed to be black. The reason for that is this reflection here. We need to keep in mind that when we have reflection of electromagnetic wave from more optically dense medium, then the phase of this electromagnetic wave changes by pi/2 radians or 180 degrees. So such phase shift causes the inversion of the originally expected interference pattern, which we would expect if we have real two slits, like two light sources of monochromatic light. However, since in this reflection experiment we have the case when light is reflected from optically more dense environment, which is obviously our mirror, then phase shift is changing by 180 degrees. So actually it's not pi divided by 2, but pi, sorry. So, we need to change the sequence of bright and dark fringes of this interference pattern. So now another option which can cause interference effect to happen, and that what we actually observe quite often in our everyday life, is interference in thin films. So if we have probably the most common example, if we have some oil on water surface, since oil possesses lower density, it forms a very thin layer on top of water. Oil and water possess different refractive indexes. And in this case, we can consider this thin film of oil on top of water as a potential condition for observing interference, some effects, which what we see when we look at certain angle to such a system, that white light is split into colorful interference peaks for different wavelengths. So we obviously observe interference maxima, where for each wavelength it is observed at different angle because of different refractive index for each of these wavelengths. So we eventually observe refractive maxima at different angles, and that's why this kind of reflected white light from such a system with a thin film, like oil film on top of water, eventually we also observe some interference pattern. So how does it work? And in order to understand that, let us consider the system when we have a thin film. Oops. So it will be n equal to unity, n, and here n again equal to unity. So we assume that we have some thin film freestanding in air. So just one freestanding thin film. Then we have some incident light. Which is reflected. But also we have some refracted beam, which goes into the film and is reflected from the other interface when we have film-air interface. So it goes down here, and then it goes up. Again, it is refracted, so we also get some reflection from here, goes down. But we also have refracted beam, which is now parallel to the initially reflected beam. So we have beam number 1 and beam number 2. It is important to highlight here that this first reflection happens from more optically dense medium at the interface with more optically dense medium. So that means that we have phase shift, like delta V, of 180 degrees for this reflected beam 1. For reflected, like refracted, and then like twice refracted beam 2, we don't have this because it is reflected once here, and here it is refracted from the interface with less optically dense interface, like medium, because here n is equal to unity. Obviously, refractive index of this film is higher. So the second beam goes from optically more dense medium to the interface with optical less dense medium. It's refracted there. And in this case of refraction from the interface with less optically dense medium, we do not observe this phase shift. So that's why only beam 1 experience this phase shift because of reflection. So now let us consider that this incident light possesses some wavelengths lambda and lambda n wavelengths in the medium of the thin film will be lambda divided by n. So we know this from the fact that the speed of electromagnetic wave is reduced inside the some medium with refractive index n. So that's the number which shows in how many times speed in this medium is smaller than that in vacuum of electromagnetic wave. And since because of conservation of energy, frequency of electromagnetic wave does not change, wavelength is changing. That's why we will have different wavelengths for this light. Outside the material of the film, in air, and inside the material of this film. So now we can consider that the difference in like path difference for beam 1 and 2 should be equal if we assume that the thickness of this film is T. Then the path difference delta, assuming that this incident angle alpha is very small, we can make an assumption that this path difference will be equal to 2 times T. So actually, since this angle alpha is very small, it would be like this refracted beam should just go straight down to the opposite interface and then straight up, and it comes out from the film in the same direction as initially reflected beam. So the path difference should be equal to 2 times T. So we kind of make an assumption that this light hits perpendicularly to the, or very close to perpendicularly to this interface, like surface of the field. Taking into account this phase shift of the beam number 1, the conditions for constructive and destructive interference, they will be opposite to those conditions which we described for two-slit interference. So we can write that 2T, which is path difference, should be equal to m plus 1/2 times lambda n, where m is changing from 0, 1, 2, and so on. So that is constructive interference, or position for like condition for bright fringe observation for interference maximum. Means that we need to have some odd number of halves of wavelengths in order to get the maximum of interference. The same condition was true for destructive interference in the experiment with two slits. That is because we didn't have this phase shift of 180 degrees because of reflection. So in the contrary, if we want to consider this condition in terms of original wavelengths in the air of incident light, we need to make to take into account this relationship between lambda n and lambda. So instead of lambda n, we can substitute its expression lambda divided by n. So that will be 2 times n times t equal to m plus 1/2 times lambda. So that will be the wavelength, the original wavelength of the light before it penetrates into the medium of the thin film. Obviously, since we have this condition for constructive interference, for interference maximum, we should specify condition for interference minimum. So that will be 2 times n times t equal to m times lambda, where m also changes 0, 1, 2, and so on. So here, as opposite to, again, to this interference with 2 slits, interference minimum will require condition when the path difference consists of some integer number of wavelengths, like full wavelengths of this light, which we consider in this experiment. So now let us consider some practical application of such interference, and that is so-called anti-reflection coating, where you can find it if you take a look on some photo camera lenses or binocular lenses. You will see that they have some like colorish background on the surface, and it doesn't look like bare glass, like which is transparent and white. So this reflected light, which you can see from these optical lenses, possess some certain colors, and that is made in order to reduce reflection from such surfaces and improve, like increase amount of light which penetrates into the optical system and finally reaches the sensor of your camera, or that amount of light which can be collected by binocular or telescope and reach your eye as a detector of optical signal. Also, anti-reflection coatings are quite widely used in solar cells because we want to have minimum reflection of solar cells, of light, from the surface of solar cell and maximum absorption of this light. So we want to create such conditions when there will be minimum reflection of incident light, and most of it will penetrate into the photoactive layer where it will be absorbed, created, it will create some electron hole pairs, like photo generated charge carriers, which then can be collected in external electric circuit and produce some useful work in form of electric power. So how does it work? Obviously, we want to have some condition for minimum interference, and should observe some destructive interference, which will reduce intensity of reflected light. So let us consider such an example. Let's have some silicon, which is semiconductor material, usually used for solar cell fabrication. Its refractive index N is equal to 3.5. Then we have on top of it a layer of its oxide, silicon oxide. And the refractive index 1.5. And then we have air with refractive index unit. So if we have some incident light on this system. As we described previously, part will be directly reflected. Another part will be refracted, will go into this silicon oxide layer. Then it will be reflected from silicon oxide silicon interface, refracted again, and it will go parallel to the initially reflected light out from the field. So here will be one more refracted beam, which is actually what we want, because we want light to reach this silicon layer, be absorbed, and create photo-generated charge carriers. So here we have again beam number 1 and beam number 2. What is important here, that as we already know, initially reflected beam will change its phase by 180 degrees. So this beam number 1, because it is reflected from medium with larger optical density, with larger refractive index. And that is also true for beam number 2 in this particular case, because here in this point of reflection of refracted beam, when it goes from silicon oxide to the interface with silicon, it is also reflected from silicon with a larger refractive index N. So it also changes its phase by 180 degrees. So now we have twice change by 180 degrees. So we actually come back to the original conditions for destructive interference effect, which we have set for two-slit experiment. So destructive interference, now it would be path difference, assuming that here is thickness D of this silicon oxide layer, or let's keep it T already. So this will be thickness T. Then optical like path difference, it will be 2 times N of this silicon oxide times T. For destructive interference, it should be lambda divided by 2. So this optical path difference should be half of the wavelength of the light. And you would say, okay, there is, we need to highlight the fact that sunlight is a combination of many different wavelengths. So we observe sunlight in a quite broad spectrum. So which wavelengths should we pick up when we design some anti-reflection coating for solar cells or for some optical instruments? So of course it depends on specific application condition, but for instance, for solar cell, we can define this wavelengths based on the spectral distribution of sunlight. So if you are an optical engineer who designs such anti-reflection coating, which wavelengths would you consider from the visible spectral range? Any suggestions? Yeah, you're welcome.
Maybe That wavelength which has the most intensity in the sun spectrum.
Yeah, absolutely right. So solar spectrum, if we consider it as a function of wavelengths, let's say, and here it will be irradiance, which we will, so wavelengths, let's say, will be nanometers. And here it will be this irradiance, it will be watt per square meter per nanometer. So that is the light intensity at any given wavelength which is interesting for us. So solar spectrum will look something like this. So that is somewhere outside the atmosphere next to planet Earth. So it will be close to the black body radiation at the temperature of black body, something about 5,500 Kelvin. That's the surface of temperature, this is surface temperature of the sun. And if we consider solar spectrum radiation on the surface of the of our planet, we will see a bit smaller peak and then some like absorption bands which are caused by absorption in atmosphere, particularly large absorption is realized by presence of some water molecules in our atmosphere in IR region, near IR region, near infrared region. So what is interesting for us? Let's say we have some optical instrument, then obviously we are interested only in the visible range. So that will be somewhere from 400 nanometers to, let's say, 750 nanometers. So that will be the visible range. And obviously, as you correctly highlighted, if we make some anti-reflection coating, which is the most simple one with one layer, so of course we can make it more complicated, then it will work for broader spectral range. But with one layer anti-reflecting coating, we want to pick up the wavelengths which brings us the most of energy of this solar spectrum. So that will be something around 550 nanometers. That corresponds to green light. So when we tune it for such condition that we want to get destructive interference for the wavelength 500 nanometers, we actually can calculate what should be the thickness of this silicon film, silicon oxide film, in order to reach our goal and get destructive interference of this particular wavelength. So the thickness can be determined as lambda divided by 4 times n. That will be 550 nanometers divided by 4 times 1 point. So here was actually 1.45. 1.45. And that will be equal to 94.8 nanometers. So that is the thickness of this anti-reflection coating, which should be used in order to get distractive interference for wavelengths 550 nanometers. And obviously that gives us some gain in the amount of light which will go through this interface, because this green light will not be reflected. So what is important to underline here, you see that we deal with quite small thicknesses, which are just parts of wavelengths, but wavelengths itself for optical spectral range, for let's say visible spectral range, you see it changes from 400 to 750 nanometers. These are very small distances. And obviously we deal even with some parts of wavelengths. So that's why interference effects are widely used in practical application for measuring thickness of different transparent layers, or not transparent but reflective layers when we have some step. Because if, for instance, you have one film deposited on a substrate, so this is our substrate, then if we deposit some aluminum film on top of this system and get reflection of monochromatic light from this region where we have the film and region where we don't have film, so it will be reflected beam 1 and reflected beam 2, then because of optical path difference, we will observe some interference pattern. And by quantifying this interference pattern, like position of minimum and maximum of this interference, we will be able with very high accuracy determine thicknesses of such films. So interference is one of the most accurate technique, like instruments based on interference effects. They are the most accurate techniques to measure very small thicknesses or changes of the distances. Pretty much the most accurate what nowadays technology can offer. I would like to show you my screen now, 1 second. And here is the structure of so-called Microsome interferometer. So how it works? We have some light source, then semi-transparent mirror. So why semi-transparent? Because we can split this incident beam into 2 parts. So one will be reflected from this mirror, semi-transparent mirror. Another will go through because this mirror is semi-transparent. So we go from 1 beam to 2 beams, which travel to mirrors like already not semi-transparent, just normal mirrors, M1 and M2. So these beams are reflected, and when they come back to this semi-transparent mirror, the observer can see the result of superposition of these 2 beams reflected from mirrors M1 and M2. Since we have monochromatic light and we split them in 2 beams, the same light, then the difference in distances from mirror M1 and M2 to this mirror semi-transparent mirror M0 will define the optical path difference, which will define conditions for interference pattern which we observe. So the longer this channel is, so the larger distance between semi-transparent mirror and mirror M1 and mirror M2, the higher accuracy for such a microsome interferometer will be reached. So to highlight how precise this technology is in terms of measuring change of distance, we need to mention such recently achieved recent achievements in field of fundamental physics as gravitational waves. So the instruments which are designed for detecting gravitational waves, they are actually this Microsome interferometers, but with extremely long channels, which is like dozens of kilometers. And that is the requirement for extremely accurate measurement of distances between this distance L1 and distance L2. So the thing is that because of approaching and passing through this space where this interferometer, this instrument is located by gravitational wave, it causes consequent changes of length L2 and then L1. And in the real time, it's possible to observe like really tiny changes of these lenses L1 and L2. And by observing some changes in the interference pattern. So then you can analyze changes in interference pattern and get the change in optical path difference, which was caused by this very weak effect of gravitational wave, which is under other conditions would be impossible to detect. So this interference effect, which we considered during this and previous lecture, is indeed one of the most accurate technique to measure distances or thicknesses of different films. There are no other options to do it with with higher accuracy. So that's pretty much everything what I wanted to tell you about interference effects. So if you have any questions, you are welcome. I would like to remind you that our final exam will be on 26th of April. We'll definitely send you reminder email, but just to use this option to remind you once more. It will cover all our material starting from beginning of the semester. So with this topic, interference, we finished the plan for this semester. And I believe that we still have one online lecture scheduled for Friday, but I believe that it would be good that I don't interrupt you guys during this and the last week of the semester. You probably have already quite a lot of tasks to finish before the end of the semester. And since we covered all material and discussed it, I believe we can skip this last lecture, so you have more time to focus on other things and like actually preparing for final exam. So it will be organized in the same manner as previous midterms. So it will be we are long kappa. There will be 6 problems which cover all material. Okay, then thank you very much for attention. It was a pleasure to work with you guys during this semester. Hope to see you around once you have a chance to finally come to university. So believe that these restrictions will be lifted completely and we will have a normal studying and teaching experience in the future. Okay, then have a good day, take care, and good luck with your final exam.
Thank you. Goodbye.
Thank you very much.
Bye-bye.
Bye.
Thank you. Hope we'll see you in the fall 2020.
Yeah, looking forward. See you later. Bye-bye.
Goodbye.